Hi, Bobcats. As we start Chapter 12 here at the beginning of Chem 1342, this is the first of a series of videos that you'll be watching through the course of the semester. This particular video is going to talk about, or this particular series of videos is going to talk about Chapter 12, which is on liquids and solids. This video series is just one piece of the instruction for this course. We'll also be meeting synchronously, and you need to be reading our textbook. Our textbook is an online textbook called Integrated General Chemistry. It's part of your Sapling Learning Homework platform. And so you'll need to be watching these videos, reading the textbook, and attending our synchronous problem solving sessions. All of these pieces together contribute to your learning. In terms of exactly what it is you need to know out of each chapter, well, there will be a list of objectives. I'll present this list of objectives on the next slide for the entire chapter. As you walk through the individual videos, the objectives that are being addressed in each of the videos will also be listed at the start of those videos. And so that's like a checklist to help you focus your learning and your studying. That I think the ultimate assessment of whether or not you really know the material for this course is, can you work all of the problems start to finish without any additional resources? No looking at your class notes, no looking at CHEM, no asking the Google, just all by yourself, start to finish. Can you work the problems? Once you hit that point, you're in great shape for this course. This list of objectives tells you what it is that you need to learn out of Chapter 12. The first few deal with intermolecular forces, then it transitions to a little bit about liquids. Then we're going to look at phase changes, including heating curves and PT phase diagrams. So as you are getting ready for a quiz or for a test, if you come back and look at this list of objectives, ask yourself, do I really know what this says? So for instance, if we look at the from the bottom, 1, 2, 3, 4, the fourth one from the bottom, it says to interpret heating curves. Well, first of all, do you know what a heating curve is? And next, what does it mean? If you can sketch a heating curve, if you can tell me what states of matter are present at each point along the way, if you can show me where there's just a single phase present, where you have more than one phase, where phase transitions are happening, if you can interpret what those heating curves mean, then you can put a check mark by that objective, and you know you're ready for it for the exam. In a previous chapter, back in Gen Chem 1, you looked very closely at gases. We looked at something called the kinetic molecular theory, which talks about the motion of the particles that make up a gas. We also looked at some mathematical laws, such as Avogadro's law, Boyle's law, Charles' law, the combined gas law, the ideal gas law, all those types of descriptions. Well, our description of liquids and solids in this chapter won't be quite as extensive as all of that you did with gases back in the gas laws chapter, but we're still going to talk quite a bit about solids, liquids, and gases. We're going to talk about all of the phase transitions between these different states of matter or phases. And we're going to look at the energies that are involved. If we look at a sample of a substance and we compare its solid form to its liquid form to its gas form, the solid has the least amount of energy, the liquid is intermediate, and the gas has the most energy. But also just even the particle description is different for all of these, in that the particles in a solid have fixed assigned positions where the particles are supposed to be. In a liquid, the particles can move past each other, but they're still very close to one another like they are in the solid phase. And then in the gas phase, the particles still are moving, but now they're separated by really big distances. So we'll look at solids, liquids, and even perhaps a little bit about gases in this chapter from all these different types of perspectives. And before we jump into our new material in this chapter, I want to bring up a point from Gen Chem 1 or Chem 1341 that hopefully you remember. If you don't, it would behoove you to spend a few minutes reviewing this section from the textbook. And that question is, how do you determine if a molecule is polar? Well, the nuts and bolts of determining if a molecule is polar is to look at either the Lewis dot structure or the Vesper structure, but we do need some kind of a structure that shows us what atom is connected to what other atoms. And then we want to analyze those electron domains on the central atom, because here's the whole deal with polar molecules. Polar molecules have permanent charge separation. The electrons spend more time around one atom than they do around another atom. That's due to differences in electronegativity. They spend more time around the more electronegative atom, making that atom slightly negative. And then the atoms that they aren't spending as much time with will be slightly positive. And so it's this asymmetric distribution of electrons that makes a molecule polar. So we're going to have to look at these electron domains on the central atom in the molecule. If it's a very simple structure where you have like a single central atom with a bunch of other atoms around it, we just need to focus on that central atom. If it's a more complicated structure where you have lots of different atoms that could potentially be considered the central atom, we may need to analyze all of them to see if any piece of that molecule is polar, which then makes the whole molecule polar. Okay, so let's look at those electron domains on the central atom. If all the electron domains on that central atom are identical, then the molecule is nonpolar. But if it has two or more distinct domains, then the molecule is polar and will have that asymmetric electron distribution, and it'll have a positive side and a negative side. So let's take a look at this molecule. This is carbon tetrachloride. When you look at that central carbon atom, there are 4 domains around that central carbon. All 4 domains are single bonds, and the other atom involved in that bond in each and every case is a chlorine. So this molecule has 4 identical electron domains, and that makes it nonpolar. Let's see what else we have. Here's a very similar molecule. This is dichloro-difluoromethane. So it's still a carbon at the center like the previous example, but now instead of having 4 chlorines, 2 of those outside atoms are fluorines. Well, that means that the electron domains are different because 2 of these domains are single bonds to chlorine and 2 of these domains are single bonds to fluorine. So the fact that it has 2 distinct domains means that this molecule will be polar. If we take a look at water, water also has 2 distinct electron domains. One of them is an oxygen-hydrogen single bond. It has 2 of that type of domain, and the other type of domain is a lone pair. So the fact that this has 2 distinct types of domains makes water a polar molecule. All right, and then in the upper right, this molecule is known as benzene. Now, for a molecule to be polar, it does have to have at least 1 polar bond, and a molecule like benzene does not contain any polar bonds. We treat the bond between any 2 of the same atoms as being completely nonpolar, so all of the carbon-carbon bonds in this ring are nonpolar. And then carbon-hydrogen is the only bond between 2 different nonmetals that we consider to be nonpolar. So this molecule has absolutely no polar bonds, and so overall this is going to be a nonpolar molecule. Then over here we have acetone for our last example. Now here there are three different atoms that could be considered our central atom. They are the three carbons that are in a row making up the backbone of this molecule. But I'm going to focus on the one that's just absolutely in the middle, the center of those three carbons, which has a double bond to oxygen. When we look at its domains, one type of domain is a double bond to oxygen. The other type of domain it has is a single bond to a carbon that's involved in a CH3 group. So it has two distinct types of domains, making acetone a polar molecule. Hopefully this review hit enough that you are comfortable remembering what's a polar molecule and what is not. If this wasn't quite enough, dig a little deeper back in the earlier chapter in our textbook where we look closely at polar and non-polar molecules.